Hello, the title of this presentation is Hamiltonian Monte Carlo for Dummies. Here's a quick overview of the presentation today. First of all, why am I doing this presentation and who are the target audience? Why Hamiltonian Monte Carlo? Why not other Monte Carlo methods? I'm going to mention some great resources that have helped me learn HMC. And then I'm going to go through some worked examples, going from very simple models through to more complex models. And hopefully along the way, explaining some of the complex terminology that's used within the Hamiltonian Monte Carlo field. And finally, a brief wrap up with some acknowledgements. So why this presentation? Well, Hamiltonian Monte Carlo I think is a magical methodology. I'm interested in doing Bayesian MCMC estimation, and it really looks like it's going to change the way that I work. It's often explained through the concepts of potential and kinetic energy. So if you're an engineer or a physicist, this will probably make a lot of sense to you. But I'm actually going to present it in a slightly different way. I come from a maths and more stats background, and I'm going to be talking about more from a joint probability density function approach. Is this for dummies? No, not really, but I'm just trying to give a simple introduction for something that's not so simple. And as part of that, I'm going to educate myself and hopefully get some feedback. So who's the target audience for this? Well, it's actually people like me. You're perhaps an applied statistician or a pharmacometrician. You've got some familiarity with Bayesian estimation, with other Monte Carlo methods like Metropolis-Hastings. Specifically, you're trying to fit complex models. So for example, they're nonlinear or they're hierarchical. They've got lots of parameters that are correlated. These are not easily achieved. MCMC sampling doesn't work particularly well when you have these complex models, and that's where HMC can offer a solution. Ideally, you have some knowledge of differential equations as well. That will help you understand the Hamiltonian equations, and perhaps you're new to STAN, which is a great platform for implementing HMC. So why use Hamiltonian Monte Carlo? Well, the standard approach to MCMC and Bayesian estimation, such as Metropolis-Hastings, can struggle to efficiently explore the joint distribution of our model parameters for high-dimensional complex models. So what does that mean? It means that we're going to end up with very high autocorrelations. We're going to get some slow parameter space exploration. And the reason is that it's difficult or it's impossible to find good proposals for Metropolis-Hastings. Essentially, the shape of those joint distributions can be a little bit ugly, and if they're ugly, it's going to struggle to come up with good proposal distributions. The outcome of that is that you end up with long run times, and if you have long run times, it's going to be difficult to build the models iteratively, which is what I tend to do. So Hamiltonian Monte Carlo offers a very powerful solution to this. I got introduced to HMC because I fit a very complicated model that was taking 11 hours to fit in SAS, and it took about 20 minutes in STAN. So that's about 30 times quicker. So a really impressive performance with HMC and STAN. This is obviously an introductory presentation. I'm going to try to cover a number of things I learned along the way trying to understand HMC, but these are great resources. So a lot of the work you're going to see today is going to be based on Radford Neal's MCMC using Hamiltonian dynamics. That's a fantastic chapter. You absolutely have to read that. That's the place to go to get a good understanding there. Michael's work is also very good. The only thing that I found a little confusing was his discussion around the typical set. But perhaps that'll be fine for you. Finally, I'd mention Ben Lambert's YouTube video. He has an excellent way of presenting things, and I think you'd find that useful to look at as well. So when you start talking about HMC, a number of terms that will come up, such as phase space and divergent transitions. And as I go through the presentation, I'm going to mention some of these terms and try to explain them in simple language. So what is Hamiltonian Monte Carlo? Well, we start with the idea that we're going to have our parameters, which I'm going to refer to as theta. And here I'm talking about a d-dimensional parameter space, so I've got d thetas. And I'm going to augment those. I'm going to add in an equal number of momentum variables, which I'm going to call m1 through to md. And then the crux of Hamiltonian mechanics and Hamiltonian's equations are these two differential equations here. We have d theta dt, so the change in our parameters respect to time, and the change in our momentum parameters respect to time. And we're introducing this idea of the h, which is the Hamiltonian. And we're going to explain a little bit about what that is. the important thing to understand is that if by using these equations, we can typically explore the joint distribution space much more quickly than via other MCMC methods. One other thing just to quickly mention is if you look at the references that I highlighted before, they're using a slightly different nomenclature. I'm using theta and m because that makes a lot of sense to me. So typically the Hamiltonian is normally expressed as the sum of this potential energy and kinetic energies. So here we have this h for the Hamiltonian, the u is the potential energy, so if you're doing Bayesian estimation that's your posterior density, and the k is the kinetic energy, which is going to be based on our momentum variables. For Bayesian analysis with MCMC, you can also view this as a joint probability density function. So the math is exactly the same, but you're just maybe viewing it in a slightly different way. So here I've introduced this idea of this joint probability density function between theta and m, and it's just going to be our posterior density here times by this probability density function from momentum variables. I'm not going to go through these equations here, but you can just pause the video and take a look and understand that actually we are talking about exactly the same thing. The only other thing to mention over here is that that second differential equation has the partial derivative of the Hamiltonian with respect to the thetas, so that's actually the gradient of our posterior density. So that's going to be something that's going to have to be calculated each time you use HMC. So those equations are perhaps not so intuitive, so let's make this far less abstract. We're going to talk about a one parameter model, and we're just going to have one momentum variable. So here, for example, we have our parameter, it's a theta, and it's just from a normal 0-1 distribution. And we're going to want to obtain MCMC samples using Hamiltonian Monte Carlo. And we're going to augment that with a single momentum variable, here m, which is going to be also drawn from a normal 0-1. So over here you can see the joint contours for that joint distribution now. Here's the distribution just for theta, and here's the joint distribution for theta on this axis and the momentum variable on this axis. And sometimes when you're talking about these joint distributions in both the theta space and the m space, it's sometimes referred to as phase space. So just to try to explain those contours, just to make sure they're 100% clear, you can think about this two-dimensional display being transferred into a one-dimensional if we just focus on the theta axis, but we're making it in 2 dimensions. So Hamilton's equations allow us to travel around these contours. So that's what we're going to be talking about here. So these two differential equations essentially create this vector field that we're looking at here on the right, and that allows us to move around these contours where the joint probability density function is the same. Thus far, I've been talking about these contours. That is where the joint probability density function is constant. An alternative way of viewing this, this is the example from Michael's presentations, is the idea that we have the Earth perhaps here at the middle, and we have an orbiting satellite. So here a very drawn badly to scale moon, and we can think about the forces acting on that moon. It has a momentum which is trying to send it away from the planet, and it has the gravitational pull that's trying to bring it into the planet. And the net result of that is that vector field that we're looking at on the right, and that controls the behavior of the moon as it circles around the Earth there. So basic HMC has 3 steps. The first step is that you're going to use the current parameter value. So down here, I'm starting off on a value of minus 1.75. And the m variable has been sampled randomly, but here I'm just going to set it to a value of 1, which is that dot there. That's step 1. Step 2 is we're going to use the Hamiltonian equations to help us travel around this contour using the vector field to guide us. So we're going to do 15 steps here, and number of things we're going to be talking about here. One is the number of steps. Here we're doing 15 steps. And the other is the step size, and I'll explain what the step size is doing in a moment. And here when we talk about these differential equations, we're talking about with respect to t and time, but actually this is just a fictitious time. It's not time in part of your differential equation. At the end of the trajectory, we're only going to keep our new value for theta. So here our new value is minus about 0.65, and that's essentially it. We're just going to repeat that process again and again and again. sampling each time a different momentum variable and doing that same process. So immediately there's some complexities here. So how large should each step be? So on the left here, I'm using the E is the epsilon of step size of 0.3. And over here I'm using epsilon and step size of 0.4. And what you see here is it's making smaller steps as it goes around that contour, versus over here it's making larger steps. So one of the things that we're interested in here is understanding the role of this epsilon as we go around these contours, as we solve these differential equations. Another issue is how many steps should we take? In the original example here, we took 15 steps going around this contour, but perhaps we could have only taken 10 steps and we would have ended up in a different value. So one of the things we need to think about when we're trying to implement HMC is how many steps should we do, as well as the size of the step. One thing that I've essentially sidestepped up to this moment is actually how are we solving these two differential equations. So we have these differential equations over here, but actually I haven't talked about how we're going to solve those. We're going to go into that in a moment. But one of the things you notice is that they're imperfect. So here I've tried to highlight this part of the graph here. And as you go around from 5.5 to 6 to 7 to 8 to 9, you can see, for example, that 0.9 is a little bit off. So with these differential equations, there's no exact analytical solutions, but we can use differential equation solvers to provide very good approximations. And we're going to be trying to follow that contour around very well. And when we talk about these ODE solvers, we can also call them as numerical integrators. So one example of a numerical integrator is called the Leapfrog integrator. It's very straightforward. It's only 3 lines of code. So you can kind of Google that and just get your head around what it's actually doing. But the important thing here is to understand is as we go around these paths, it doesn't matter too much if we actually are a little bit off. Because in this case, we've fallen a little bit further out. So we've actually gone into an area where the probability density function is a little bit lower. But we can make this very easy correction. It looks something like this. So had we stopped at 0.9, we essentially look at the value of the joint probability density function for the proposal, which would be this point here, relative to the probability density function at where we started, over at 0.0 here. And if we stop, we look at that ratio, we only accept this transition with a 99% of the time. And here you can kind of write that more formally as a transition probability, that we accept the proposal with probability the minimum of these two values. This correction to the transition probability is referred to as a Metropolis update by Neal. I mentioned before that we were talking about using the Leapfrog integrator. However, sometimes the Leapfrog integrator will go wrong, and this is referred to as the divergent transitions. And this is typically where the step size is too large. So in this graph here, I'm showing you 5 steps with the Leapfrog integrator, but I'm using a very, very large epsilon here, the very large step size. So it's really struggling to follow the contour that it's supposed to be following, and it's tending to go all over the place. So what happens in this situation is that our Hamiltonian, the value of the contour, essentially, is going to be going very high, very low, very high, very low. And it's going to be easy to diagnose that. Thus, an efficient implementation of HMC requires this careful optimization of the step size. We don't want it too small so that we don't move very far at all. We don't want it too large so we have these divergent transitions. And equally the number of steps. We don't really want to be going round and round here. We can see that after 15 steps we've gone about 3/4 of the way round. If we'd gone to 20 steps we'd pretty much back to where we started. So if we're trying to explore the parameter space in our theta domain here, we're trying to work out how many steps we should be doing to explore that well. The good news for us users is that people behind Stan have developed methods to try to optimize these settings for us. So the NUTS algorithm, the no U-turn algorithm, essentially looks at these trajectories like this. And when we start to be turning back on ourselves, it then says, okay, you seem to have already explored this distribution already quite well. We should think about stopping. Another thing just to finally mention, this epsilon we talked about it being 0.3 or 0.4, but actually it should have some randomness. You could imagine here if we actually did do 20 steps all the way around, we might end up in a very similar position, and then we do another 20 steps again with the same epsilon, we end up in exactly the same position. And the danger is that we end up just repeatedly going through exactly the same loop. So it makes sense to put some randomness into that epsilon value. So thus far, we've just been talking about having a single theta, a single parameter. But now we're going to start looking at more interesting models. We're going to start with a two-dimensional case. So now we have the probability density function here for theta 2 against theta 1. And I'm just showing it for different correlations from 0 through to 0.95. So when we do our MCMC, we're going to try to get samples that are representative of these distributions using our MC or Hamiltonian Monte Carlo to achieve that. Now in this situation, actually even though these distributions are pretty thin and pretty ugly, it's actually not a problem for standard Metropolis-Hastings, because if our proposal for the standard Metropolis-Hastings looks like these joint distributions here, we're going to have no problems obtaining very good samples. However, in this case, now we have a relationship between theta 2 and theta 1 that isn't multivariate normal. So now it's actually got this kind of curved relationship or banana-shaped relationship between the two parameters. And the difficulty here is it's going to be very, very difficult, if not impossible, to come up with proposal distributions for the Metropolis-Hastings that's going to be able to effectively explore this joint distribution of our model parameters. And that's where Hamiltonian Monte Carlo will really come in and help us out. So now we're going to consider example 2, and this is going to be a two-dimensional space for theta. So we're going to have a theta 1 and a theta 2, and we're going to have a high correlation between those two thetas of 0.95. And this is the example that Radford Neal considers in his book chapter. So what you're looking at here in this graph is figure 5.3 taken directly from his book chapter. And at the bottom you see my reproduction of that graph. So we have theta 2 against theta 1 in this graph. We have M2 against M1 in this graph. And we have the value of the Hamilton against the step size in the third graph. And we're going to look a little bit more at this model and its behavior. One thing to note here is that the trajectories are truly smooth. So in the bottom panel here we have 25 steps with an epsilon of 0.25. And you can see the movement is a little bit choppy. In the top graph we're doing 10 times more steps with an epsilon that's 10 times smaller. And you can see the evolution of the parameters over time is much more smooth. You can also see that in the terms of the value of the Hamiltonian. So the ability to trace that contour very neatly and accurately is much more superior in this example here with the larger number of steps and the smaller epsilon than it is down here. You see the Hamiltonian is changing much more markedly. The disadvantage, of course, with the larger number of step sizes and the smaller epsilon is that you're having to do a lot more computing to get very similar types of results. So that's why we're trying to find this balance between the number of steps and the size of the epsilon. So for this problem, in total now we have our 4-parameter space. We have our theta 1, theta 2, M1 and M2. So it's much more difficult to see the contour when we look at our bivariate plots here. So we have theta 2 against theta 1, M1 against theta 1, theta 2 against theta M2, and M1 versus M2. We're not seeing these nice ellipses like we were before. But if we look at the value of the Hamiltonian, which is shown here in black, against the step size, we see that the value of the Hamiltonian is approximately constant. But we see our thetas in these graphs and our m's in these graphs are changing markedly. Another way to view that is to think about the contribution of the potential energy, the U here, and the kinetic energy, the K, to that overall value of the Hamiltonian. So for example, at step 8, we are near the mode of the posterior density. So for a bivariate normal distribution, that would be 0, 0. And we see our theta 2 and theta 1 are both very small. So the overall contribution, shown here in green, to the value of the Hamiltonian is very small. And most of the contribution to the Hamiltonian is coming from the kinetic energy, which is the blue here. And that's where we see that M2 is actually quite small, but M1 is very large. and that's where the overall contribution to the Hamiltonian is coming from. However, at step 17, most of the contribution to the Hamiltonian is coming from the potential energy, and very little is coming from the kinetic energy. So up here we can see that the value of θ1 and θ2 are both large and positive, whereas the two momentum variables here, m1 versus m2, are both very small. So again, we're getting this idea of we're transferring between contributions from the thetas and contributions from the momentum variables, and that's why we're having this ability to explore the joint parameter space for our thetas extremely well. It's just worth mentioning, if we do 1,000 steps, we can see this cyclic nature of Hamiltonian Monte Carlo. So here we have our θ1 parameter across 1,000 steps, our θ2 parameter across 1,000 steps, and you see it going from around -2 all the way up to about +2 and then back again. So again, it's going up and down and up and down. We can see similarly for our momentum variables, m1, m2, and because if we superimpose those four figures above, our m1, our θ1 and our θ2 are highly correlated, and that's why they're having this kind of characteristic pattern of following each other, because they're highly correlated. An important property of the Leapfrog integrator is that the trajectories are completely reversible. So using any what's called a symplectic integrator, such as the Leapfrog, will ensure this concept of reversibility. So what does that mean? So it means if we started at this point here, like in our example for our bivariate normal, and we did our 25 steps, we're going to follow a certain path, and we ended up at position 25. Now if we do the exact opposite, we start at the position 25 and do 25 steps, we exactly trace out exactly the same journey and finish back where we originally started over here. So this idea of this reversibility, plus the concept of the Metropolis update, the idea we adjust for any changes in the value of the Hamiltonian, the value of the joint probability density function, that satisfies the concept of detailed balance. So for any 2 points here, so we're talking about our current point and our proposal point, we have this idea that the joint probability density function for our current value times by our transition probability is going to be equal to the probability density function for our proposal times by the transition from our proposal to our current. So you can go back and look at the earlier slides and you can just see that that equation holds true. Another important property of the Leapfrog integrator or any symplectic integrator is the concept of volume preservation. So here we have 4 points being mapped out in a little black box, and what we're going to do is we're going to trace those round for 15 steps, and we can think about the volume of that region at step 0 there. Now as we progress each of these 15 steps of our Hamiltonian Monte Carlo using the Leapfrog integrator, the volume of that region in each of those boxes is going to be exactly the same. So I view this as a result of the transformations in theta and the momentum space being shear transformations. So the Leapfrog integrator essentially is 3 steps. It does a transformation of the momentum variable, then it does a transformation of the theta variable, and then it does a transformation of the momentum variable. And you can think of these as essentially 3 shear transformations. So here we're doing a shear transformation in the x domain, so the y domain isn't changing, and down here we're doing a transformation in the y domain. And if you look at these matrices that create this operation, the determinant of this is just 1. So we're not changing the underlying size of the box here. So thus far we've only considered quite simple examples, but what about more complex problems? So one thing when we're thinking about the difficulty of working with a particular model, we can think about the condition number of the correlation matrix. The higher this value, the more difficult it's likely to be to work with. So with the 2-parameter model and a correlation of 0.95, we get 2 eigenvalues, and we can look at the ratio of those and work out the condition number for that matrix is 39. Now we're going to consider a more difficult situation, a multivariate normal again, but with 5 parameters and a correlation matrix as shown below here. This correlation matrix has a condition number of about 145, And you see that there's a very strong correlations between parameters 1 and 2, strong correlation between parameters 4 and 5, and parameter 3 has a positive correlation with parameters 1 and 2 and a negative correlation with parameters 4 and 5. So just to view that graphically, this 5-parameter example, if we just simulate from that correlation matrix, we can see this very strong correlation between 1 and 2 and a strong correlation between 4 and 5. And we see that theta 3 has this positive correlation here and a negative correlation here. So this is starting to look like a more complicated model to work with. So now what we're going to do is we're going to look at 12 random sets of momentum variables just to start looking at how this Hamiltonian Monte Carlo behaves. In each of these 12 situations, we're going to start initially from the posterior mode. So each of our 5 parameters here, this is theta 1, theta 2, theta 3, theta 4, theta 5, are all starting at 0, but they're being given different momentum variables in each of these graphs. So in this first graph, we have our 5 momentum variables. What we can see here is the force momentum variable is large, it's minus 2.35. That corresponds to theta 4 here, which is the light blue. And what you see is that the value of theta 4 starts decreasing a lot because it has this negative value here. The number after the 2 bars is just the sums of the squares of these values. So what you see here in this first example, we have quite a large value, so we see our parameters changing quite a lot. In this example, number 5, we see that the 5 momentum variables are all quite small, and if we combine that with our initial starting at the posterior modes, the parameters that are not going to change a lot in this example. So if we look at some of the interesting ones here, we can see again with 2 large negative momentum variables in this 8th replicate, theta 1 and theta 2, which are both highly correlated, are going to start off going very, very negative before returning and coming back. So we see that the marginal distributions, kind of the minus 2s and the plus 2s, are being well explored in this example, but not necessarily in this example here, when we start from this initial condition. However, more likely we'd actually be starting from a position away from the mode, so there's going to be much more energy in this system, more potential energy. And we see here across our 12 replicates much more variation across the marginal distributions for each of our 5 parameters here. So we can see that we're doing a good job of exploring the marginal distributions for each of our 5 parameters. So as a final example, I'm going to consider Radford Neal's 100-dimension problem. So in this case, he's looking at 100 parameters. We have theta 1 through theta 100. We have therefore 100 momentum variables. And the covariance matrix that he's using is shown below here. The condition number is this ratio of the largest eigenvalue to the smallest eigenvalue, which would be just this 1 divided by 0.01 squared, so it's about 10,000. So along the diagonal here we have essentially the standard deviations for the 100 parameters. So this one has a standard deviation of 1 all the way down to this guy down here. He just has a standard deviation of 0.01. And in his example he uses 150 steps with a step size of around 0.13, but with a plus or minus 20% from one iteration to the next. And he does 1,000 iterations. So it's difficult to look at all 100 parameters here, so I'm just going to focus on theta 1 and theta 2, the 2 with the largest standard deviations, 1 in the middle, and then the 2 with the smallest standard deviations. Okay, so what we're going to do is we're going to look at the first 12 HMC iterations. We're going to focus specifically on these graphs for theta 1 and theta 2. Theta 1 is the red and theta 2 is the orange. And we start off here in iteration 1 and all the parameters are starting at 0. And we're going to try to follow the red line here, which is actually hidden behind the orange, this first iteration, because the 2 momentum variables just by chance happen to be very similar. But then we start following it through at the end of the second iteration, through the third and through the fourth. At each iteration we resample a new set of momentum variables, and that allows us to explore those marginal distributions here. So we see the red starting to go towards positive values and down towards negative values across these first 8 iterations. At the 9th iteration we again sample a new set of momentum variables, but actually at the end of this 9th iteration, this is actually rejected. So the 10th iteration we see here, basically if we just focus on this box here, it starts at exactly the same place as the 9th iteration, but with a new set of momentum variables. And at the end of the 10th iteration, it gets accepted, and we carry on through the 11th and the 12th. Now on these graphs you can see theta 1, theta 2 and theta 50, because the standard deviation here is about 1 and here it's about 0.5, but we can't see theta 99 and theta 100 because they're much smaller standard deviations. So we just focus on the first 4 iterations here, but with a different y-axis for each of the different thetas. Here we see theta 1 going up towards about 0.5 and then down to minus 1. We also see for theta 2 some good exploration of the marginal distributions. And we can see what's happening now with theta 99 here in the light blue and theta 100. And we're getting this much faster oscillation. So we're getting much more movement up and down for theta 99 and theta 100. So what does this look like for our trace plots? We've done 1,000 iterations now, and at the end of the iteration we either accept the new value or we reject it. And what we can see here was with theta 1, it's on the top panel here, through theta 2, and then with these smaller standard deviations, theta 99 and theta 100. And first of all we can see that the trace plots look really good. There doesn't seem to be a high autocorrelations here. So here what we can see is the autocorrelation plots for theta 1, theta 2, theta 50, theta 99 and theta 100. And what we see is at a lag of just 2 or 3, the correlations are essentially down to 0 for all of our parameters. And if we summarize our parameters here, the sample means should be close to 0, and that's what we see. And we see that the sample standard deviations for theta 1 should be about 1, and it is. Theta 2 is around 1, and it is. And theta 50 is around 0.5, and theta 99, theta 100 are 0.02 and 0.01. So everything's looking pretty good for a fairly complex model there. And the rejection rate that I got was 12%, which I think is very similar to Radford Neal. I think he reported 13%. So even for this complex model, Hamiltonian Monte Carlo is doing a great job with very low autocorrelations being generated. One thing I was interested to better understand was how Radford Neal's 100 parameter problem that we've just been looking at compared to real models that I've worked with. So with Radford Neal's 100 parameter model, the condition number was 10,000. I have these two models down here. The condition number is a little bit lower, so that's showing that his problem is potentially a little bit more tricky. What I was interested to plot was the percent of the eigenvalues that you're using versus the total variance explained. So if you use 100 parameters here, you have 100 eigenvalues. If you use all 100% of those, you explain all the variation in the data. But if you used the first 25 eigenvalues for Radford Neal's example, you're explaining about 50-55% of the total variation in that data. So I did the same exercise here, but with these 382 parameters. I have 382 eigenvalues, and I can plot again of the fraction of those total of the 382 eigenvalues, how much variation I'm explaining for these two different models. And what we see here is we see this kind of fairly similar shape between what Radford Neal considered and the two models that I looked at. Just to mention that if everything was perfectly uncorrelated, the correlation matrix, we'd have points along this line here. So the further away we are from this line, generally the more tricky it would be. Some final notes about HMC. Basic HMC, as I've shown here, is very much the foundation, but it's not the final implementation for efficient HMC in practice. So for example, what's used in STAN. So we have these trajectories. There's no need to specifically restrict ourselves to only using the final step. We can consider the whole trajectory. These trajectory lengths can be optimized so that no U-turn sampler is going backwards and forwards to essentially make sure we're doing a good job of exploring, but that we're not doubling back on ourselves and wasting additional computing time. We need to think about whether we should scale our parameters and the momentum variables to ensure good performance. And also, one of the things I've not discussed a lot here is the calculation of the gradients, but good software will use automatic differentiation to ensure both fast and accurate calculations of those gradients. So as a summary, I would say as a tool for Bayesian estimation for complex models, I think Hamiltonian Monte Carlo looks superb. So I'll finish up and just give some acknowledgements to Radford Neal, Michael and Ben for putting their information out there, helping people like me understand it. Very much appreciated. If you have any comments, any corrections or suggestions about this video, please let me know at this email address below.